Welcome to the debate. Imagine for a moment that every time you typed a simple question into a search engine, the lights in your neighborhood dimmed slightly.
That is a terrifying thought.
Right? I mean, it sounds like complete science fiction. But honestly, if artificial intelligence had just continued on its original trajectory, that was kind of the physical reality we were hurtling toward.
Yeah, absolutely.
When we look back at the history of, say, aerospace engineering, the early days were entirely defined by brute force. If you wanted to get further into space, you built a bigger rocket.
Just massive amounts of thrust.
Exactly. You packed it with more fuel, you ignited it, and you basically hoped the sheer scale of the explosion would push you through the atmosphere.
And, for a long time, the AI industry operated on that exact same philosophy. The whole, the scale is all you need era.
Right. No one was overly concerned with the elegance of the architecture or like the thermal limits of the data center. The singular goal was just packing more parameters into the model and throwing more raw electricity at the training run, just to see what kind of emergent behaviors would unlock.
But eventually, just like in aerospace, you hit the unforgiving limits of physics and economics.
Yes, you do. You cannot simply keep building bigger rockets. You have to start engineering for structural efficiency, reusable components, precise orbital mechanics. And looking at our source material today, it is overwhelmingly clear that the artificial intelligence landscape has reached that exact inflection point.
A massive paradigm shift.
Yeah, we are rapidly shifting away from that initial race for raw brute force parameter scale, and we're entering a highly complex, multi-dimensional model war.
A war that is fundamentally forcing the entire tech ecosystem to reconsider what it actually means to build a functional, deployable AI system in the real world.
Exactly. And the source material outlines two distinct, incredibly powerful forces driving this new era. On one side, there is this aggressive drive for operational efficiency and cost reduction.
Right.
On the other side, there's the pursuit of highly advanced dynamic reasoning capabilities happening directly at the point of inference. So the central question we are exploring today is this: which of these two forces is the true defining factor of modern AI development?
It's a huge question.
It is. And my position is that operational costs, inference memory bottlenecks, and extreme efficiency, what the industry calls total cost of ownership, those fundamentally dictate the future of AI infrastructure.
And my position is that this new era is actually defined by the pursuit of complex, dynamic reasoning capabilities. I'd argue that efficiency is merely a prerequisite to afford massive test-time compute.
Okay, so let's lay out our perspectives here. The way I read the current landscape, the battleground is now entirely defined by economic feasibility, hardware-level constraints, and just, well, operational utility.
Sure, the practical realities.
Right. We are seeing a massive shift where developers are actively moving away from deploying those massive, monolithic, compute-heavy foundational models. And the reason is simple mathematics. They are just prohibitively expensive for production-grade infrastructure.
They definitely burn through capital.
They do. If you look at the material, the true innovations defining the field right now are optimization techniques, things like low-rank adaptation, or LoRa, and ultra-low-bit quantization. We're talking about specifically pushing down to FP4 and NT4 precision formats.
Well, I understand the financial appeal of that argument, I really do. But when you rely so heavily on aggressive quantization, you are essentially amputating the model's highest cognitive functions.
I wouldn't call it amputating.
I mean, you kind of are. You're taking a brilliantly trained neural network and squashing its weights just to save a few bucks on cloud compute. And that irreversibly degrades its ability to handle edge case reasoning.
I see why you think that, but let me give you a different perspective on how quantization actually functions mathematically. Because it's far more elegant than just, lobotomizing the model.
Okay, I'm listening.
Think of a neural network's weights like a high-resolution, uncompressed 4K photograph. Every single pixel has millions of color gradients, which obviously takes up massive storage. Quantization is the process of converting that photograph into like a highly stylized pixel art painting. You lose the exact decimal precision of the color gradients, essentially squeezing 16 bits of memory down to just 4 bits. But the broader structural patterns remain entirely intact. You still clearly see it's a picture of a cat.
Right. but it's a blurry cat.
But by doing this, we enable multi-billion parameter models to run locally on standard consumer-grade hardware. This preserves data privacy because you don't have to send sensitive enterprise data to a cloud server, and it eliminates network latency. The goal isn't just making the model smarter, it's making it economically feasible to exist in the real world.
I hear that.
If a model is too heavy to run, its intelligence is purely theoretical.
That is a fair point about local deployment. Privacy is a big deal. But I would argue the true frontier isn't just taking existing static models and shrinking them down for laptops.
Then what is it?
The true frontier is the rapid convergence of entirely new reasoning architectures and synthetic data pipelines. We are shifting toward post-training reasoning paradigms. I'm talking about test-time compute scaling, tree of thought search, and the integration of Monte Carlo tree search.
Okay, getting into the heavy algorithms.
Exactly. Because instead of standard autoregressive generation, where the model just, blindly predicts the next most likely word in a sequence based on statistical probability, these new architectures dynamically allocate additional inference compute based on the complexity of your prompt.
Right, they take more time to think.
Yes, total cost of ownership is important, yes. But shrinking a model is simply a mechanical trick to clear up room on the GPU. We are making that room so we can deploy massive amounts of compute at this time. This allows the model to generate thousands of hidden thought tokens, critique its own logic, and traverse decision trees to solve previously unsolvable mathematical and software engineering problems.
But see, when we talk about letting a model generate thousands of internal thought tokens to verify its own logic, we immediately crash into the physical hardware-software boundary.
How so?
Because you cannot discuss test-time compute without acknowledging inference memory bottlenecks. As context windows expand into the hundreds of thousands, or even millions of tokens, memory bandwidth, specifically the key value or KV cache, becomes the absolute choke point of the entire operation.
Well, sure, because to predict the next token accurately, the model has to hold the mathematical representations of all previous tokens in its active memory.
Exactly. Let's visualize what the KV cache actually is for a second. Imagine a human trying to read a deeply complex 10,000-page legal document.
Sounds exhausting.
Right? But to understand the very next word on page 10,001, they have to consciously hold every single previous word they've ever read in their active working memory, all at the exact same time.
Right.
Doing that digitally for 1 million tokens consumes a staggering amount of video RAM. The model isn't starved for compute power, it's starved for memory access. That is why the most critical engineering breakthroughs right now are architectures like grouped query attention and multi-head latent attention.
Which are explicitly designed to mathematically compress that KV cache.
Yes, and we have to talk about custom kernel acceleration like flash attention.
Which is a brilliant piece of engineering, I'll concede that.
It is absolutely revolutionary. To explain it simply, a GPU has two types of memory: a massive, slow pool of memory and a tiny, lightning-fast pool right next to the processing cores. Without flash attention, the processor acts like a chaotic chef in a kitchen, running back and forth to the refrigerator to grab a single ingredient, chopping it, and running back for the next one.
A lot of wasted movement.
Exactly. Flash attention optimizes the memory blocks, so the chef brings all the ingredients to the cutting board at once, maximizing what we call tensor core utilization. The entire engineering stack is furiously oriented toward bridging the gap between raw calculation speed and real-world memory bottlenecks. Efficiency is the master here, not reasoning.
See, I come at it from a completely different way.
Okay,
The only reason we need these incredibly sophisticated memory optimizations like flash attention, or even techniques like speculative decoding, is to buy enough headroom for that dynamic compute allocation I mentioned. Let's look at speculative decoding, because I actually think it proves my point beautifully.
go ahead.
In speculative decoding, you take a tiny, fast draft model to quickly propose a sequence of, say, 10 or 20 tokens, and then a massive target model validates all of them simultaneously in parallel.
Right, which drastically accelerates the tokens per second generation rate for the end user.
Yes, but why do we actually need that blistering speed?
Because users hate waiting?
Well, sure. Not just so a chatbot feels slightly more responsive, though. We need it because the reasoning architectures of the future require generating vast chains of internal logic before the user ever sees a final answer.
Ah, I see where you're going.
If we don't optimize the KV cache, if we don't deploy speculative decoding to speed up the hidden token generation, we literally cannot afford the computational time required for deep internal verification. Efficiency isn't the end goal. Efficiency is the servant. It is the scaffolding being built to support the actual monument, which is advanced reasoning.
That's an interesting point, though I would definitely frame it differently. Focusing primarily on pushing the absolute frontier of reasoning is sort of like designing a hyper-intelligent, world-class scholar who can solve the mysteries of the universe, but takes 3 weeks and $1 million of funding just to answer a single question.
That's a bit of an exaggeration.
But it's computationally impressive in a lab, right? Yet it is completely impractical for the real world. Let's actually look at the impact of inference computing on engineering students entering the field right now.
Oh, the university curriculum has certainly shifted.
It has entirely transformed. When we analyze university programs today, students aren't just learning how to prompt massive cloud models or build clever user interfaces, they are being forced into the deep end of profiling GPU memory.
True.
They are rigorously analyzing operational costs versus model performance. They quickly learn that if you are designing a system with sub-second latency requirements, like say a real-time high-frequency trading algorithm or a live customer service voice agent that needs to interrupt and respond naturally,
Right.
that hyper-intelligent scholar model is utterly useless to you. The performance metrics that actually matter to an engineering student today are tokens per dollar and milliseconds of latency. The financial and memory constraints dictate that they must deploy a quantized, highly efficient model.
I don't disagree that latency and operational costs are critical constraints for a student building a real-time trading bot, but the tasks the industry is preparing these models to perform are moving far beyond rapid-fire API calls. We are asking them to act as autonomous digital agents.
Okay.
We want them to write code, test that code, spin up a server, and deploy an application entirely on their own. And that requires a fundamental architectural shift toward deep reasoning.
Which brings us directly to the architectural battle playing out on the silicon right now. Because again, I look at the material and I see innovations entirely focused on solving computational complexity, not just making models quote-unquote smarter. We are seeing a massive pivot toward mixture of experts, or MOE, designs.
The challenge with MOE routing, though, is the risk of knowledge collapse. If the model misinterprets the prompt and routes the query to the wrong expert subnetwork, the hallucination is immediate and severe.
That's a known risk, yeah, but the efficiency gains make it entirely worth solving. Instead of activating every single parameter in a dense model for every single word, which is wildly inefficient, an MOE model uses learned routing layers to direct the input to just a few specialized neural networks.
Right, it partitions the workload.
Exactly. You maintain a high parameter capacity, maybe a 70 billion parameter model, but you drastically reduce the active compute per token. You might only activate 10 billion parameters at any given moment. In parallel to MOE, we are seeing the rise of hybrid state space models, or SSMs, things like Mamba and RWKV.
Which are fascinating attempts to bypass the transformer architecture altogether.
They are. They exist to solve the quadratic computational complexity of traditional transformers. In a standard transformer, if you double the size of the document you're analyzing, the compute required doesn't double, it quadruples.
It's an exponential scaling wall.
Exactly, a wall. State space models enable linear time context processing. Instead of looking back at every single previous token, they compress the context into a fixed-size state tracker that updates dynamically. That mathematical shift means you can suddenly process millions of tokens, like a full repository codebase or a multimodal video stream in real time without melting the GPU. It is an efficiency play through and through.
That's a compelling argument, but have you considered the data wall?
The data wall?
Yes. Structural efficiency, whether it's through clever MOE routing or linear time state space models, means absolutely nothing without high-quality data to fuel it. And as the source material prominently highlights, we have essentially run out of high-quality, human-generated data. The entire internet has effectively been scraped and consumed.
We have exhausted the passive digital exhaust of humanity, yes.
Precisely. So how do we push the frontier of intelligence when there is no more data to read? Reading laboratories aren't just tweaking algorithms, they are building massive, proprietary synthetic data factories.
Right.
And this is where the reasoning paradigm truly takes over. They are using smaller, highly specialized verifier models and automated theorem provers to generate, critique, and filter dense, error-free reasoning data sets at a scale that humans could never produce.
See, I'm not convinced by that line of reasoning because you kind of just made my argument for me.
Wait, how so?
Notice what you just said. They are using smaller, highly specialized models. The fact that the most advanced labs are utilizing swarms of micro models to verify data perfectly proves my point about operational efficiency and targeted utility winning out over massive, unwieldy reasoning engines.
I'm sorry, but I just don't buy that. Let me tell you why. You are conflating the manufacturing process with the final product.
How?
Yes, they are using smaller verifiers, but they are using them during the training and data generation phase to create the complex reasoning traces needed to teach the larger primary models how to think. They are generating synthetic logic trails. The end product of that factory is a frontier architecture capable of deep, dynamic reasoning at inference.
Okay, I see your point.
The structural efficiencies you mentioned, like Mamba or RWKV, are scientifically fascinating. But if a linear time model cannot match the sheer algorithmic accuracy and reasoning depth of a heavily trained synthetic data-backed transformer, it will just be relegated to niche, low-stakes use cases.
Democratizing these state-of-the-art capabilities, and developers are realizing they don't need a monolithic superintelligence to solve business problems. Modern software pipelines are rapidly transitioning toward multi-agent orchestration. We are building networks of specialized micro-models operating under agentic frameworks.
But multi-agent loops are notoriously brittle.
They are getting more robust by the day, precisely because we are optimizing them for cost. In a modern pipeline, you might have one highly quantized 8 billion parameter model that solely handles natural language parsing.
Right.
It routes tasks to another ultra-efficient model specialized in SQL that queries a database, while a third model formats the JSON output. Because they are running in a continuous ecosystem together, total cost of ownership and extreme energy efficiency will ultimately dictate survival. If you tried to use your massive reasoning model for every step in a 10-step agentic loop, your API inference costs would bankrupt the project before it solved the problem.
Well, again, look at the engineering students. Step 1 of system design is now calculating the inference cost per query. Operational cheapness isn't a bonus, it's a structural requirement for multi-agent systems to exist.
Operational cheapness is important for a toy project, certainly, but let's look at what is actually required for seamless multi-agent orchestration in enterprise environments.
Okay, you need models that can execute software tools flawlessly. You need models that can recognize obscure edge cases, correct their own logical errors on the fly, and maintain complex continuity across multiple steps. That requires the absolute optimal frontier of algorithmic accuracy.
But if they can't afford to run it,
In a 10-step agentic workflow, a single hallucination or logical failure in step 2 doesn't just produce a slightly wrong answer. It cascades into a catastrophic failure by step 10. When an engineering student eventually deploys a system that handles live financial transactions or autonomous medical diagnostics, the rigorous reasoning verification provided by test time compute is entirely non-negotiable. Deep reasoning will always trump mere operational cheapness in high-stakes scenarios.
but again, you are ignoring the physical reality of the hardware. If the memory bandwidth isn't there, the system crashes regardless of how smart it is. If the KV cache overflows because your high-stakes medical system is generating too many internal thought tokens, you don't get a highly accurate diagnostic answer, you get an out-of-memory error.
Nobody wants that.
Exactly. The system panics and halts. That's why the material explicitly ties the future of AI to architectures that can deliver extreme energy efficiency and sub-second latency alongside their accuracy.
Well, I don't dispute that an out-of-memory error is a hard stop. Where we fundamentally diverge is on the primary driver of the field's evolution. You view quantization and memory optimization as the defining innovations of this era.
Yes.
I view them as necessary plumbing. The true building, the actual paradigm-shifting architecture being constructed above that plumbing, is the post-training reasoning paradigm. It's the ability of the model to pause, search through a Monte Carlo decision tree, simulate a dozen different outcomes, evaluate them, and then confidently act.
Okay, let's unpack that Monte Carlo tree search integration because it perfectly illustrates exactly why cost and efficiency govern everything.
Sure.
In a traditional setup, inference is a one-way street. The model predicts tokens sequentially, moving forward. With tree search, you are asking the model to explore branching paths of logic simultaneously.
Exactly. It evaluates multiple potential next steps, assigns each branch a mathematical probability of success based on its synthetic data training, and pursues the most promising path while pruning the dead ends.
Right. And mechanically, on the silicon, that means you are multiplying your compute cost at inference by a factor of 10 or 50 or 100, depending on how deep the search tree goes. Every single branch requires its own memory allocation.
Yes, it is computationally heavy.
Every single evaluation step requires reading and writing to the GPU's high bandwidth memory. If you don't have FP4 precision formats allowing that massive reasoning model to sit entirely within the VRAM of local accelerators, the latency of moving that data back and forth across a network makes the tree of thought search devastatingly slow. It becomes too expensive to ever use.
Which is exactly why the industry is pushing so incredibly hard on both fronts simultaneously.
But if you ask an AI researcher what gets them out of bed in the morning, it's not the prospect of saving 3 cents on API calls or reducing the power draw by a few milliwatts.
No, but it is unlocking the ability for an artificial intelligence to solve a novel, previously unsolved mathematical theorem by dynamically thinking through the problem at inference time. Synthetic data factories that are breaking the data wall, the test time compute scaling, these are what will fundamentally elevate AI from a probabilistic parlor trick into a genuine, autonomous digital workforce.
And if you ask a chief technology officer or that engineering student we discussed who's trying to actually build and deploy a sustainable business model, they will tell you that a model that costs $100 per query to run is just a science experiment.
That's a bit cynical.
But it's true. It doesn't matter if it can solve a novel theorem, if it bankrupts the company doing it. As AI moves from experimental proofs of concept into deeply integrated production-grade infrastructure, the true innovations, the ones that actually touch our daily lives, are the parameter-efficient fine-tuning, quantization, the memory optimization, and the state space architectures that make deployment economically feasible, fast, and private.
I still say efficiency is just a tool to buy time and space. The real revolution is allowing models to think dynamically, to self-correct, and to reason beyond their initial training data.
Well, it seems we are analyzing two sides of the exact same silicon wafer. But I think there is a profound point of convergence here that we both clearly see. We both acknowledge, and the source material explicitly confirms, that the era of simply scaling up parameters with brute force compute has drawn to a close.
Absolutely. The whole scale is all you need philosophy got us off the launch pad, but it will not get us to the next paradigm. Inference phase innovation, whether you view it primarily through the lens of hardware efficiency or through the depth of dynamic reasoning, is unequivocally the new critical battleground for the entire industry.
This transition is incredibly complex, and there is still so much more to explore in the source material, particularly regarding how these multi-agent frameworks will ultimately organize themselves to execute tasks in enterprise environments. We won't declare a definitive winner today between operational efficiency and advanced reasoning.
Too early to tell anyway.
Exactly. We will leave it to our listeners to weigh the cold realities of computational costs against the incredible promise of dynamic cognitive capabilities.
It is a fascinating trade-off to consider as the technology evolves.
It really is. It brings us right back to that aerospace engineering metaphor we started with. We have finally stopped just building bigger, more explosive rockets. Now we have to figure out how to actually navigate the intense complexities of orbit, whether that means perfecting the fuel efficiency for the long haul or designing the most sophisticated navigation computer possible to chart the unknown.
Thank you for joining us.